Hello friends, welcome to my lecture on evaluation of real integrals using residues. Now here we are going to consider some special kind of real integrals where we need to take a different kind of contour, different from the ones which we have studied so far. The contour will depend on the problem, it changes from problem to problem. So, let us see, we will now illustrate some show some examples, and there we shall see how some certain types of real integrals can be evaluated by making a suitable choice of contours other than those considered earlier. So, let us consider this integral 0 to infinity e to the power minus x square dx. We know that by using gamma function the value of this integral is root pi by 2. So, using this value of integral 0 to infinity e to the power minus x square dx, let us find the value of the integral 0 to infinity e to the power minus x square cos 2 alpha cos x square sin 2 alpha dx, and simultaneously we will also get the value of integral 0 to infinity e to the power minus x square cos 2 alpha sin x square sin 2 alpha dx. So, this is 0 root pi over 2 cos alpha, and this is root pi over 2 sin alpha, and here when you will take alpha equal to pi by 4, you will get integral e to the power minus x square cos pi by 2. Cos pi by 2 will be 0, so e to the power 0 will be 1, and we will get cos x square sin pi by 2 is 1. So, we will get integral 0 to infinity cos x square here, and here when you take alpha equal to pi by 4, you will similarly get sin x square. So, integral 0 to infinity cos x square, integral 0 to infinity sin x square will be equal to root pi by 2 cos pi by 4 sin pi by 4, which each of the cos pi by 4 sin pi by 4 have value 1 by root 2. So, we will get root pi over 2 root 2. So, by taking alpha equal to pi by 4 in A and B, we get C. Now, let us see how to get the value of A and B integrals by using residue calculus. So, let us consider the contour integral over C e to the power minus z square dz, where the contour C consists of the arc of the circle mod z equal to r from A to B. So, let us draw the contour. So, this is origin, okay. Let me take this as A, and let us say this is B, okay. So, then where the contour C consists of the arc gamma of the circle mod z equal to r, this is gamma, okay, arc of the circle mod z equal to r from A to B, 0 less than or equal to alpha less than or equal to pi by 4. So, alpha lies between 0 and pi by 4, the line BO and the line OA, this line OA and the line BO, okay. So, this is 0 x y. So, our contour is contour is the line OA, the arc gamma and the line BO, okay. Now, e to the power minus z square dz, e to the power minus z square is an analytic function within and on this contour C. So, we have integral over C e to the power minus z square dz equal to integral 0 to r. Now, you see this AB is the arc of the circle with mod z equal to r. So, OA is equal to r. So, along OA z is equal to x, and therefore, we have integral 0 to r e to the power minus x square dx, then integral along gamma e to the power minus z square dz, and then integral from r to 0. We are coming from B to 0. So, integral from r to 0. Now, z is equal to rho e I alpha, along BO z is equal to rho e to the power I alpha, where rho varies from r to 0, rho varies from r to 0. So, we get e to the power minus rho e I alpha square e to the power I alpha. Every point z on the segment OB has argument alpha, okay, and let us say magnitude rho, okay. So, z equal to rho e I alpha we put here, and then dz equal to e to the power I alpha into d rho, because alpha is constant, okay. So, since on BO z equal to rho e I alpha and rho varies from 0 to r, we are coming from r B to 0, so we are writing r to 0, okay. Now, mod of, now let us show, let us find the value of the integral along gamma, the semi part of the circle, mod of z equal to r. So, integral over gamma e to power minus z square dz is less than or equal to r. Let us put z equal to rei theta. Any point here on the arc, okay, I can write z equal to r e to the power I theta. Okay. So, z equal to r e I theta, when we put, we get e to the power minus r square e to the power 2 I theta, and then dz equal to r e to the power I theta into I d theta. Okay. So, r is constant, it comes here, then 0 to alpha mod of e to the power minus r square e to the power 2 I theta. Okay. E to the power minus r square e to the power 2 I theta is cos 2 theta plus I sin 2 theta. So, mod of this is equal to e to the power minus r square cos 2 theta, because mod of e to the power minus I r square sin 2 theta is equal to 1. Okay, so, this is e to the power minus r square cos 2 theta, and then mod of I and mod of e to the power I theta is 1. So, we get this. Okay. Now, here we put first phi equal to pi by 2 minus 2 theta. Okay. In this integral, let us take phi equal to pi by 2 minus 2 theta. Okay. Then what you get, sin phi equal to sin pi by 2 minus 2 theta, which gives you cos 2 theta. So, for cos 2 theta we write sin phi, and you also notice that d phi equal to minus 2 d theta. Okay. Theta varies from 0 to alpha. Okay. So, when theta is equal to 0, phi is equal to pi by 2, and when theta is equal to alpha, we get phi equal to pi by 2 minus 2 alpha. Okay. Pi by 2 minus 2 alpha we denote by beta. Okay. So, what do we get? Integral 0 to alpha e to the power minus r square cos 2 theta d theta will be replaced by, for 0 we get the limit pi by 2, for alpha we get the limit beta, e to the power minus r square cos 2 theta becomes sin phi, and d theta becomes minus d phi by minus 2. So, this is 1 by 2, and the limits of integration can be changed with this, because of this minus sign. So, we get beta pi by 2 e to the power minus r square sin phi d phi. Okay. And r was already there outside. So, we get 1 by 2 r integral over beta to pi by 2 e to the power minus r square sin phi d phi. Since, let us look at this, alpha lies between 0 and pi by 4. Therefore, 2 alpha lies between 0 and pi by 2. So, beta is greater than or equal to 0. Because of this condition, beta is greater than or equal to 0. Beta is greater than or equal to 0. So, integral over beta to beta to pi by 2 we have, and we know that, as we have seen earlier, sin phi is greater than or equal to 2 phi over pi. Okay. When phi belongs to the interval 0 to pi by 2, Jordan inequality. Jordan's inequality. So, we have put here, for sin phi we put 2 phi over pi. So, we get e to the power minus 2 r square phi over pi. Okay. So, from here we come to this. Okay. Now, mod of integral over gamma e to the power minus z square dz is less than. Okay. So, we have just integrated here e to the power minus 2 r square phi over pi. When you integrate, you get e to the power minus 2 r square phi over pi divided by minus 2 r square over pi. Okay. Because we are integrating over with respect to phi. So, we, and 1 by 2 r is outside. So, we get 1 by 2 r, and then we get pi upon 2 r square from here, and then we get the we put the upper and lower limits, we get e to the power minus 2 r square beta over pi minus e to the power minus r square. Now, when r goes to infinity, what will happen here when r goes to infinity? This is when r will cancel, we get pi over 4r, okay, pi over 4r e to the power minus 2r square beta divided by pi, okay, minus e to the power minus r square, okay. And beta, as you have seen, beta is greater than or equal to 0, okay. So, even if beta is equal to 0, when beta equal to 0, this becomes 1. So, 1 minus e to the power minus r square we have, and when r goes to infinity, this goes to 0, okay. This is suppose 1, then 1 minus 0 is 1, and then 1 over r here is there. So, 1 over r goes to 0, and therefore, this goes to 0 as r goes to infinity. If beta is greater than 0, then this goes to 0, this goes to 0, and this also goes to 0. Okay. So, as r goes to infinity, integral over gamma e to the power minus z square dz goes to 0. Now, in the equation 1, let us go to the equation 1. So, in this equation, as r goes to infinity, what happens? This becomes integral 0 to infinity e to the power minus x square dx, and this goes to 0, and we get here infinity to 0 this quantity. Okay. Let us see what is this. Okay. So, when r goes to infinity, this is integral 0 to infinity e to the power minus x square dx. Okay. This quantity becomes integral 0 to infinity e to the power minus x square dx. This is known to us. It is root pi by 2. So, what do we get? This we are using. So, so this becomes, this is root pi over 2. Okay. Root pi over 2. So, root pi over 2, and this goes to 0, and then we have infinity to 0 e to the power minus rho square e to the power 2 I alpha into e to the power I alpha d rho equal to 0. Okay. So, when it goes to the other side, the limits will change to 0 to infinity. So, this becomes 0 to infinity e to the power minus rho square 2 e to the power 2 I alpha into e to the power I alpha d rho equal to root pi over 2. And then you put e to the power 2 I alpha as cos 2 alpha plus I sin 2 alpha, and here you put here for e to the power I alpha you put cos alpha plus I sin alpha. So, we get this. So, okay, so no, e to the power I alpha we bring to the right side, and then integral 0 to infinity e to the power minus rho square cos 2 alpha plus I sin 2 alpha d rho is equal to root pi by 2 e to the power minus I alpha. This e to the power I alpha which was here comes here because it is independent of rho. So, then 0 to infinity e to the power minus rho square cos 2 alpha into e to the power minus I rho square sin 2 alpha, that is cos rho square sin 2 alpha minus I sin rho square sin 2 alpha d rho equal to this. Now, let us put real and imaginary parts. This is root pi by 2 cos alpha minus I sin alpha. So, then integral 0 to infinity e to the power minus rho square cos 2 alpha cos rho square sin 2 alpha d rho is equal to root pi by 2 cos alpha, and 0 to infinity e to the power minus rho square cos 2 alpha sin rho square sin 2 alpha d rho equal to root pi by 2 sin alpha. So, this proves part A and B, and as I said, part C can be obtained from here by taking alpha equal to pi by 4. Okay. So, we get part C. Now, integral over C e to the power minus z square dz, where C is the boundary of the rectangle with vertices at minus a plus ib, minus a plus ib, and letting a tends to infinity. Let us evaluate this integral. We are given that this is equal to root pi by 2. So, you can see here we have this contour. This is minus a 0. Let us take a here, and then this is a plus ib, and we have minus a plus ib here. Okay. So, let us take this segment minus a to a as C1, this segment as a to a plus ib as C2, from a plus ib to minus a plus ib is C3 and minus a plus ib to minus a as C4. Okay. So, our contour C consists of 4 parts. Okay. The 4 parts are C1, C2, C3, C4. Okay. So, we will evaluate the integral over C e to the power minus z square dz along all these 4 parts. Okay. To evaluate the integral over C e to power minus z square dz, which is equal to 0, because C is a simple closed curve and e to power minus z square is analytic in the whole complex plane. So, it is analytic inside and on this contour C. Okay. So, let us find this integral. So, integral over C fz dz, where fz is e to power minus z square and C is given here. C as I draw there, let us draw again here. Okay. So, what we do is the integrand is analytic inside and on C, therefore, by Cauchy integral theorem, integral over C fz dz equal to integral over C1 plus integral over C2 plus integral over C3 plus integral over C4 is equal to 0. Okay. Now, for evaluation along C1, okay, let us draw here now. Now, you can see when we want to integrate along C1, the line segment from minus a to a lies on the real axis. Therefore, for z we shall write x, okay, and fz is e to the power minus z square. So, we will write x for z. So, e to the power minus x square dx, and x varies from minus a to a. Now, e to the power minus x square is an even function of x. So, it is 2 times 0 to a e to the power minus x square dx, and when a goes to infinity, okay, when a goes to infinity, the limit of this is 2 times integral 0 to infinity e to the power minus x square dx. So, when a goes to infinity, this becomes 2 times root pi by 2, that is root pi. Okay. Now, let us integrate along C2. So, for evaluating along C2, now let us look at this. For along C2, x remains constant, x is equal to a, y varies from 0 to b. So, we can take any point z here, the z can be written as a plus iy, okay, where y varies from 0 to b along C2. Okay. So, on C2 we have this. So, let us use this. Z equal to a plus ib, y varies from 0 to b, then integral over C2 fz dz is equal to integral over 0 to b, fz is e to power minus z square. So, e to power minus a plus iy whole square, dz is I dy. Okay. So, I dy be put, and then e to power minus a plus iy whole square is a square minus y square plus 2iay. So, we get e to the power minus a square minus y square into e to the power minus 2aiy and then dy. This I we have kept outside. Okay. For evaluating along C3, now let us look at C3. Along C3, you notice that this y is fixed. Okay. Y is equal to b. Okay. X varies from a to minus a. Okay. So, on C3, we will write z as x plus ib. Okay, where x varies from b to minus, varies from a to minus a. Okay. So, we put x plus ib, x varies from a to minus a. So, along C3 we have, now from a to minus a we can make it from minus a to a, but we have to put negative sign here. So, minus integral over minus a to a e to the power minus z square. So, e to the power minus x plus ib whole square and dz equal to dx. So, we put dx here. So, minus integral over minus a to a, you can now square this. So, then x square minus b square and then we get e to power minus 2I Vx dx. And when we integrate along C4, you notice again that bi is fixed, okay. Bi is no, bi varies, x is fixed, x is equal to minus a, okay. So along C4 z is equal to minus a plus Iy, where bi varies from b to 0, okay. So we get z equal to minus a plus Iy, bi varies from b to 0, and therefore integral over C4 f z dz is equal to minus integral over 0 to b. It was from b to 0. When we want to make it 0 to b, we put negative sign. So minus 0 to b e to the power minus z square. Z is minus a plus Iy whole square, dz equal to I dy. Okay. So this is minus I and then integral 0 to b e to the power minus a square minus bi square, then e to power 2I ay dy. Okay. Now let us combine equation 4 and 6. Okay. 4 is this one. Okay. 4 is this and 6 is this. When you combine C2 and C4, what do you get? You notice that e to the power minus I a square minus bi square, and this is same here. Okay. So let me combine integral over C2 plus integral over C4 f z dz. This gives you minus I times integral over 0 to b e to the power minus a square minus bi square, a square minus bi square, and e to the power 2ai ay, and then here minus e to the power minus 2ai by dy. Okay. So this is minus I times integral over 0 to b e to the power minus a square minus bi square, and this is 2I times sin 2ay. Okay. So dy. So this is what we put here. Okay. This is 2 times I square becomes minus 1. So 2 times 0 to b e to the power minus a square minus bi square sin 2a by dy. Now let us estimate the value of I star. So mod of I star is less than or equal to 2 times 0 to b e to the power minus a square minus bi square. This is positive quantity. Then mod of sin 2ay, mod of sin theta is less than or equal to 1. So this is less than or equal to 2 times b into e to the power minus a square plus b square. Okay. Now how we get this? You can see here sin this quantity e to the power minus a square minus bi square is e to the power minus a square plus bi square. Okay. So e to the power bi varies from 0 to b, and e to the power bi square is an increasing function. So e to the power bi square will be less than or equal to e to the power b square. So this quantity is less than or equal to e to the power minus a square plus b square, and therefore this is less than or equal to e to the power minus a square plus b square into 2b. Okay. So 2b e to the power minus a square plus b square. Now when a goes to infinity, okay, e to the power minus a square goes to 0. So this quantity goes to 0 as a goes to infinity. So C2 and plus C4, okay, when a goes to infinity go to 0. Now what is left? We are left with integral along C1. Integral along C1 we have already found, it is root pi. Okay. So integral along C3, okay, C3 is this. Okay. Let us concentrate on this. So we get now root pi minus integral of, okay, when a goes to infinity this becomes minus infinity to infinity this quantity. Okay. So root pi minus this. Okay. So root pi minus integral over minus infinity to infinity e to the power minus x square minus bi square e to the power minus 2I Vx dx equal to 0, and we can put it as cos 2Vx minus I sin 2Vx. So minus infinity to infinity e to the power minus x square minus bi square cos 2Bx minus I sin 2Bx dx equal to root pi. Now comparing real part on both sides, because we want to evaluate the value of integral over minus infinity to infinity e to the power minus x square minus bi square cos 2Bx. We ultimately want to get this. So we just need to evaluate the and compare the real part. So minus infinity to infinity e to the power minus x square minus b square cos 2Bx dx equal to root pi. Okay, and this is a real quantity. So, if you imaginary part, if you equate, the imaginary part will have value 0. Integral over minus infinity to infinity e to the power minus x square minus b square sin 2 bx dx, this will be equal to 0. Okay, or we can say integral over minus infinity to infinity e to the power minus x square sin 2 bx dx equal to 0. You can divide this equation by e to the power b square. Okay, and this has to happen because this is an even function, e to the power minus x square is an even function, sin 2 bx is an odd function. So, its value over minus infinity to infinity has to be 0. So, that is verified. Now, this is equal to root pi. So, we can now write it as e to the power minus x square into e to the power b square. This e to the power b square we can take to the other side, and this is root pi into e to the power minus by square. Now, e to the power minus x square cos 2 bx is an even function. So, we can make it 2 times 0 to infinity. Okay. So, 0 to infinity e to the power minus x square cos 2 bx dx is root pi into e to the power minus b square divided by 2. Okay. So, with that I come to the end of this lecture. Thank you very much for your attention.